All right, today, exponential functions. Exponential functions would be your e to the x. And this is actually, we're going to look at the derivative and the integral. This is actually the easiest derivative rule there is. I promise.
I like that.
Feel like you're being fooled?
A little bit, but
The derivative of e to the x is e to the x.
And that's all
This
we
is like
learned
one of my
today.
favorite
Do our homework,
rules.
go
That's
home.
the unit
Told you it's the easiest one.
Yeah.
This means that the integral of e to the x dx is e to the x plus c. So,
I like this rule.
here is your graph of e to the x, something like this. You should vaguely remember some back there somewhere, right? That exponential growth curve. Well, think like this. All right, what's the slope of the tangent line over, around, in here?
Very small. Like almost zero.
Very small, almost zero, and approaching that zero. Everybody agree? Okay. And it starts getting a little bit bigger than zero. And right here, the slope of the tangent line is actually 1. And then starts getting bigger. So here's the actual derivative graph. It's the same graph.
I like this.
Slopes mirror that same graph. Now, anything else we've done still comes into play. So for example, we use the chain rule every single time we're finding a derivative. So chain rule still comes into play. Here's the inside piece. The derivative of x is 1, so it doesn't affect anything here. But if that wasn't just a single x, well, then that chain rule is going to come into play because it won't be a 1. Some different things like that. If we see this guy involved in a product or quotient, well, we saw the product rule and the quotient rule. Nothing's changing on that. So let's look at some derivatives first. If I wanted the derivative with respect to x of e to the 3x minus 1. Well, the derivative of that exponential function is still that exponential function. So it would be e to the 3x minus 1, but then times 3. Where did the times 3 come from? Chain rule. Derivative with respect to x of e to the sine x. Now, we're not used to necessarily seeing a trig function sitting up there as the exponent on an exponential, but it doesn't matter. The derivative of an exponential is still that same exponential, e to the sine x. Then the chain rule, derivative of sine x is cosine x.
I like this rule.
Are you okay with that? So if I said the derivative with respect to x of e to the negative x, this would become negative e to the negative x. It's still e to the negative x, chain rule, times negative 1. I just moved the negative in front. So this is correct too. A lot of times we do see if we just have a coefficient move to the front, but it really doesn't matter. Everybody okay there? Okay, let's bring in a couple other pieces here. Let's go derivative with respect to x of x squared e to the 2x. Now this would be our product rule. X squared is my first term. E to the 2x is my second term. So I'm just following through with my product rule. First, x squared. Derivative of the second, e to the 2x times 2. Plus the second, e to the 2x times derivative of the first, 2x. Derivative of x squared is 2x. Those old rules, they're still there. Nothing's changing on that. Nothing at all. As far as simplifying, not really anything I can do. See, 2x squared e to the 2x plus 2x e to the 2x. Sometimes you'll see in an answer key where they'll factor out the common factor. I don't know if that's really worth it or not, but just gotta be apprised that that could happen. Like I could take out a 2x e to the 2x. Leaves me x plus 1. No, I don't have to, but we can see different forms of the same answer. Everybody okay there? Okay. Here's one of our newer ones. Derivative with respect to x of the natural log of 1 plus e to the x. That natural log derivative is one of our newer ones, so we're going to go 1 over what we were taking the natural log of. So we'd have 1 over 1 plus e to the x. Chain rule, the derivative of 1 plus e to the x would be 0 plus e to the x. Okay there? Let's see, we've had power, chain, product. Let's get a quotient up here. Let's go e to the 2x over 3x squared. The quotient rule. You can see the division. So our old quotient rule was bottom, derivative of the top, minus top, derivative of the bottom over the bottom squared. So bottom, derivative of the top, e to the 2x times 2, minus the top, e to the 2x, derivative of the bottom, 6x, over the bottom square, which would be 9x to the 4th, 3x squared squared. Now we can do some simplifying, but that's the raw form of the derivative there. And as far as the simplifying, it looks like I could take a 3 out of each part, because 3 goes into 3, 3 goes into 6, 3 goes into 9. And I could take an x out of each part. Because I have an x over by the 6. An x squared here, an x to the 4th, so x. I guess I'll move that 2 up front. 2x e to the 2x minus 2x e to the 2x. Nope, sorry, it's 2e to the 2x over 3x cubed. I took out that x by the 6. One thing else I really could do is I could factor out a 2e to the 2x up top, but it's not going to cancel anything. Are you okay there? All right. So if we're going backwards, the integration. Looks pretty simple. The integral of e to the x is e to the x plus c because it's indefinite integral. Nothing new there. Okay. The key is this guy right here. I need this nice single variable. If I don't have that single variable, there's where the U-substitution is going to come in. So nothing new as far as a U-substitution. We've seen it before. So if I had the integral of e to the 3x dx, I know I need just an x there, not a 3x. That's what's causing the problem. So we're going to go u equals 3x. du then is 3 dx. Now I don't have a 3 dx. I've got a 1 dx. So what do we have to do to that 3? Divided by 3. There we go. So we'd have 1/3 integral e to the u du. Now it's back to that simplistic integral. The integral of e to the u would be e to the u. So we'd have 1/3 e to the u plus c which would be 1/3 e to the 3x plus c. Okay there? Okay. Let's go e to the negative x. Let's put a 2 out here. 2e to the negative x dx. Kind of give us a look with a coefficient out there. The coefficient out front, we want to remember, isn't really affecting anything we're doing. Our focus is what we're actually integrating, which is e to the negative x. I need that positive x right there, not a negative. So there comes still that U-substitution. We're going to let u be negative x. du would be negative dx. Now we'll get that e to a single variable, in this case e to the u, inside the integral. We can take care of the negative by bringing it to the other side, which is just going to negate the 2 out front. So I'd have negative 2 e to the u plus c. Put my u value back in, negative 2 e to the negative x plus c. You okay there? Now sometimes we do get some looks that just don't look very good to us. We need to focus on the fact that if I see an e to something other than just an x, I'm going to have to think of some sort of U-substitution. So when I first glance at this one, yeah, it looks difficult and I'm not quite sure what to do, but I know this much. I can't have a square root x sitting in that power. I need just an x. So there's my logical place to place the u. I can try it. So if u equals square root x, du would be 1/2 x to the negative 1/2 dx. If that fits, I'm good to go. If it doesn't, I'll back up and start over. But that's my first thought, is I really want a single variable up here, not a radical, not a power, not a coefficient, nothing. So we got to see if this guy works. It actually will. Might not look the best in that form. If I rewrite it, drop in that negative, it looks like that. I've got my root x on the bottom where I wanted it. Dx out to the side, that's fine. Where I'm running into the problem is on that 2, but I can get rid of the 2. Remember, we can multiply the 2 over. So this 2 can come over, and I would be left with 1 over root x. So I'd have 2 integral e to the u du. Now it's a simple integral. Was not looking so simple. Had to go through the substitution, but then I get back to this guy. So yes, I do think that this is the easiest integral you're going to do, but you have to get it in that form to do it. All right, so still that substitution's coming back in. So you got to still do some work sometimes. 2e to the u plus c, which is 2e to the root x plus c. So if I see anything up in the power on an e other than a singular x, that is my first thought of where the u should be. Very first thought. Now let me give you a situation where that first thought doesn't necessarily work. And that's okay. My first thought when I look at this, I've got e to the 2x over 1 plus e to the 2x. My first thought is, wait a minute, I don't want the 2x there. I want just a single variable. So my first thought is, I'm going to let u be 2x. Du then would be 2 dx, and that's not going to work. I don't mind the 2. It doesn't bother me at all. I can divide the 2 over, but I'm not able to get rid of that. Now I've got e to the u over 1 plus e to the u. It's still not in any basic form that I can integrate. That's why I'm saying it wouldn't work. Sometimes I don't know till I try. And we've said this before. Sometimes when you go to substitution, the first thing you try to substitute just doesn't work. It's okay. My next option would be to let u be e to the 2x. It'll generate the e to the 2x, but won't take care of the 1. So that's not going to help me. My next choice would be let u be 1 plus e to the 2x, and this one's going to help me. Because this will give me 2e to the 2x dx. I've taken care of the bottom. It's now a single variable. I've taken care of the top. Let me say I've taken care of the top because I've got this right here. Again, I'm not worried about the 2. I got this guy. Fitting for that guy. All right, I can get rid of that 2. So I would have 1/2 to get rid of the 2. Integral 1 over u du. Now this is back to an integral I know. And what was the integral of 1 over u? Is that natural log? All right, so we'd have 1/2 ln absolute value of u, which would be 1 plus e to the 2x plus c. Are you okay with that? The nice thing is the e derivative, pretty basic, quick. The e integral, pretty basic, quick. We have to sometimes get it in that form. Right, get this nice basic integral right here. So we have to do some substitution or other to make that happen. Sometimes when we're doing that, we end up in another basic form. Still something we've done. Ain't nothing new there. Okay? The derivative, if I wanted the derivative of this, e to the 3x times 3. Derivative of this, e to the negative x times negative 1. I could have that chain rule coming in. If I wanted the derivative of this, that's going to be a quotient rule. I can see the division. So we've got 2 pieces we're adding in to all the stuff we're doing. They're not difficult ones as far as some of the other stuff we've done, I don't think. Pretty quick, but all the other rules still apply. Anything else that we've done?